Assalamualaikum warahmatullahi wabarakatuh and good morning. My name is Muhammad AMIRUL FIRDAUS bin Muhammad RAWI. My number matric B122310220. Today, my group excited to present the subject Control Principle BERE 2363. And the title for today, Electromechanical Control System. And my lecturer name, Sir Ahmad Faiz bin Zainal Abidin. And my group section 2BERT 1/2. You can see this is my group logo. My name group set kita jangan pecah, and tagline stay positive. Electromechanical control system is my Gantt chart for my group. Gantt chart has 12 tasks. Task 1, briefing and division of the task. Task 2, determine the specification to fulfill the criteria. Task 3, draw function block diagram. Task 4, draw schematic diagram. Task 5, block diagram with mathematically equation. Task 6, find overall transfer function. Task 7, analysis and test. Task 8, complete and submit the report. Task 9, slide presentation making. Task 10, record video presentation. Task 11, edit the video. And last task, submit the video. And you can see the responsible, plan and actual at the Gantt chart. My table of content for my group. 1. Introduction. 2. Block diagram of the plan. 3. Time domain analysis of the plan. 4. MATLAB, code and output. 5. Stability analysis of the plan. 6. General block diagram of the control system. 7. Electromechanical drawing of the control system. 8. Hardware costing. 9. Mathematically modeling. 10. Overall transfer function. 11. Time domain analysis of the control system. 12. Stability analysis of the control system. And last, conclusion and reference. First, introduction. The control principle to design a simple electromechanical control system. The system convert electrical energy into mechanical energy. To design an analysis a simple electromechanical control system using 9-step method and MATLAB simulation. There are 3 basic elements: mass, damper and spring. The plan of the system is of second order transfer function, comprising mass, damper and spring, having torque and angular displacement as input and output. The main design requirements of the project are for stability, no or minimum overshoot.
Hello and good day. My name is LUQMAAN bin ZULKIFLI. My metric number is B122310015. We start by dive the meaning and control system. The plan refers to the system or process that we aim to control. In this slide, show the block diagram of the plan that we represent from chosen transfer function. This represents the plan's transfer function in the system. The output TMS is processed by the plan to produce the output theta ms. The transfer function illustrates the relationship between the input and output in the Laplace domain, providing a frequency domain representation of the system behavior. This is crucial for understanding how the system responds to different inputs. Moving on to slide 8, we get into the time domain analysis of the plan. First, we calculate the natural frequency of the system. We get 10 rad per second. This tells how fast the system oscillates in the absence of damping. Next, we determine the damping ratio, which is calculated as 0.01. This low damping ratio indicates that the system is underdamped. We then calculate key time domain metrics. Settling time is approximately 40 seconds. The peak time is 0.3142 seconds, representing the time it takes to reach the first peak of the response. The rise time is approximately 0.158 seconds. The system is underdamped with a percentage overshoot of about 9.69%, indicating how much the system exceeds its final value before settling. Finally, we analyze the steady state error, which is 0.9991, indicating good accuracy in reaching the desired output. Now we move on to slide 9. We analyze the step response of the closed loop system using MATLAB. The transfer function is defined with specific numerator and denominator coefficient. The MATLAB code also calculates and displays the step response information including rise time, settling time, overshoot, and steady state error. This comprehensive analysis helps in evaluating the system performance and stability. Thank you for your attention. That's all for me.
Hello, my name is Loong and my matrix ID is B122310142. And now we'll be covering the MATLAB output. Step response plot shows that the system is stable, is a well-damped behavior. The absence of overshoot and undershoot shows that it is not oscillatory, and the settling time is quite short. This shows that the system reaches steady state quickly. And here we will be covering the stability analysis of the plant. So based on the Wolff-Hurwitz criterion table, the total number of poles is 2, because this is a second order system, and the poles in the left half plane is determined by the Wolff-Hurwitz criterion you can see here. Meanwhile, on the right half plane there are no poles, and there are also no poles in the imaginary axis. Since all the poles lies in the left half of the plane, the system is stable. So next is the general block diagram of the control system. So we will have the input, error detector, controller, actuator, plant, and the sensor. So the controller is the amplifier, the actuator is the DC motor, the plant is the mechanical system, and the sensor is the tachometer. So based on the block diagram, we can create the electromechanical drawing of the control system. So for this closed loop control system, the objective is to maintain the desired output of the system. So it begins with the input or the desired parameter, which is then being compared with the actual parameter that is measured by the sensor in the detector, which will identify any errors. The controller processes the error and sends the signals to the actuator, which then will adjust the plant or the mechanical system to correct the output. The output is then measured again by the sensor to create a feedback loop, which is special for the closed loop system, and this ensures the system continues to adjust to match the desired parameter. These cycles allow the system to maintain stability and accuracy.
Hi, I'm IZZUDDIN bin RAHIM. My metric number is B122310525. On my session, I'm going to continue the slide. Firstly, I'm going to break down the hardware costing for the project I'm being working on. Let's take a look at the component and their prices. Here's the breakdown. For number 1, we use 3 registers, which is 20 ohm, 100 ohm, and 2 ohm, each costing Rm50 For number 2, we use an operational amplifier or op-amp for Rm390 For number 3, we use 2 capacitors, which is 1 millifarad and 2 millifarad, each at Rm70 For number 4, we use 2 inductors, which is 1 millihenry and 2 millihenry, both priced at Rm150 For number 5, we use a high-back EMF DC motor for Rm2530 For number 6, we use a mass of 0.01 kg for Rm12 For number 7, a damper spring and height feedback tachometer costing Rm415
Rm5.30
and Rm415 respectively. The total hardware cost come to
Rm61.40.
Secondly, I'm going to dive into the mathematical modeling behind this setup. We're using an operational amplifier, resistor, and capacitor to calculate the PDI control transfer function. First, the proportional terms, which is P. We use R1 is 20 ohm. Next, the integral term, which is I. We use R2 is 1 k ohm and C1 is 1 millifarad. The transfer function for the integral term is 100 per S. Then, the derivative term, which is D. We use R3 is 2 ohm and C2 is 1 millifarad. The transfer function here is 0.004 S. Combining this, the overall transfer function become 20 plus 100 per S plus 2.5S. We also using the height back EMF DC-2 with a transfer function of 7.5, and for the mechanical system we have mass of 1.1 kg, a damper of 5 Ns, and spring with a stiffness of 100 Nm. Now we got the mathematical sort. Let's move to the overall transfer function in the next part. In this final part, we are going to explore the overall transfer function in our system. This is where all the component elements we discussed come together to define how the system behaves. Let's break down the equation that define this behavior, which is 20 squared plus 200s plus 1000 per s cubed plus 30 squared plus 300s plus 1000. This is the transfer function in our system. It describes the relationship between the input and output in frequency domain. Let dissect it step by step. For number 1, we find the numerator, which is top part. The numerator is 25 squared plus 200s plus 1000. This represents the system response to change the input. The s squared term indicate acceleration, and the s term represent the velocity, and the constant term, which is 1000, relate to steady state response. For number 2, we find the denominator, which is bottom part. The denominator is s cubed plus 30s squared plus 30s 300s plus 1000. This defines the system stability and dynamic. For the s squared term relates to inertia, and the s term account the damping, and the constant term 1000 ensure the system reach the steady state. When we combine this term, we get a system that responds quickly to change and also stabilize smoothly over the time. That's it. The system is perfect. Example how engineering principles comes together to create something. And that's it. We gone for hardware costing to mathematical modeling, and finally the overall transfer function. The system is perfect example of how engineering principles comes together to create something functional and efficient. Thanks for watching.
About time domain analysis of the control system. Okay, we start by examining the system transient response, which is crucial for understanding how the system behaves over time. For our system, we use the OTF function, which is here, as you can see, 25 s over 2 s to the power of 2 plus 200s plus 1000. For the denominator is s to the power of 3 plus 30 s power of 2 plus 300s plus 1000. Okay, first we identify the parameter of the system, which is the Wn, or the frequency is 10 rad per second, and the damping ratio is 1, which is for critically dampened. Okay, now for the transient response, the rise time is taken for the 10% to 90% of the final value. For the second order, we got the formula, which is rise time Tr equal to 1.8 over Wn. So we substitute the value and we get the rise time equal to 0.18 second. Next, the settling time for the time taken within 2% of the final value, which is settling time equal to 4 over damping ratio times Wn, frequency response. Okay, and then we substitute the equation and we get 0.4 second. Next, for the delay time, which is time taken for the response reach 50% of the final value, and we get the formula, which is 1 plus 0.7 multiplied with the ratio divide with the frequency response, and we got the delay time is 0.170 second. Next, we calculate the maximum overshoot, which is the peak value of the responsive relative to the final value. We use this formula for the maximum overshoot, and we substitute the value, and we get it is equal to 0. And for the maximum overshoot, as the percentage of overshoot, we just calculate, like take the maximum overshoot and multiply with 100%, and we will get 0% of the overshoot. Okay, next, the peak time for the system. We can define the peak time because it is critically damped, so it cannot be defined. Next, we need to find the steady state response. Firstly, we find the error constant, which is position error constant. We use this formula and we substitute with the 0 as with the 0, and we will get the same answer, which is 1. Also with the velocity error constant and the acceleration error constant, also will get 1. Next, for the steady state error, or the short one is SSE. Okay, we just take what we calculate just now, which is the error constant, and put into the formula, and we will get this equation, which is 1 over 1 plus, it should be Kp here, but still the same. We just take this value and substitute it, and we will get 1 over 2 or 0.5. Same with each other, RAM input and parabolic input acceleration error, we still get the 0.5. Okay, next, for the stability analysis of the control system, we using Rode-Horowitz criterion table. So from this OTF, overall transfer function, we get this table. Okay, this mathematical method help determine whether all the root of the system characteristic equation lie in the left method, left half of the complex plane, which is essential for the stability. Okay, for like we can see here, all these pole are in the left hand pole, which is good. That's mean our system is stable. Okay. Okay, next, for the conclusion, our project successfully implement control engineering principle design a stable and efficient system. The system met all design objectives, including no overshoot and minimal steady state error. Looking ahead, I hope that we can explore advanced control technique and application for more complex electromechanical system, and improve our project to become more suitable, that can also make a use for the industry. And last but not least, this is our reference, which is the one that helped us during our project, and for the that help we to find info to make this design. Okay, that's all from us. Thank you so much.